In my fourth example of finding the area between two curves, we're going to see an instance where the representative rectangle is going to be horizontal and see how that plays out in solving of the problem. So when I look at my two functions, the first thing that I notice is that they're both given in the form of x equals. The first one says x equals 3 minus y squared. Now, if you took Algebra 2 and studied conic sections, you might recognize this as a sideways parabola. Let me just write this in a slightly different way and it might become more apparent to you. What we have here is a parabola that opens to the left because of the negative out in front and has a vertex of 3, 0. Remember, for sideways parabolas, you read the vertex backwards from the way that you did when it was a y equals parabola. So I'm going to go ahead and draw a parabola that opens to the left with a vertex at 3, 0. Okay, the second curve also is an x equals, but this is just a line that has its terms scrambled up. If we write this as y equals negative x plus 1, this will seem very familiar to you. So this has a y-intercept at 1 and a negative slope. Okay, now at this stage of the game, I would usually draw in the representative rectangle. I would draw in a rectangle that would connect top to bottom. But as I scan this region here, starting at the left and going to the right, way over to the left, red's on top and blue's on the bottom. And as I scan over to the middle, red's on top, blue's on the bottom. But as I get all the way to the right, it's red over top of red. And that's not going to work. There's no way you can subtract a function to itself and be able to find that area in between. So for this reason, I'm going to have to switch my perspective and go from top minus bottom. That's really the best way to handle this. So what I'm going to do is I'm going to draw my representative rectangle horizontally, connecting right and left side. Now, there's going to be more implications to this as we go on and set the problem up. But to find the area of this region, and maybe I'll go ahead and shade that region green like I have for the other problems so you know exactly what I'm looking at. To find this area, I'm going to set up the formula area equals, it's going to be a definite integral. Now instead of being top minus bottom, it's going to be right minus left. And the right curve is the parabola, or 3 minus y squared. The left curve is the line, y plus 1. And the question that I've asked myself in the other examples were, which axis is this representative rectangle perpendicular to? And if we were to continue this brown rectangle to the left, it would go through the y-axis. So it's perpendicular to the y-axis, which makes this a dy problem. And one more implication of that is going to be for the limits of integration. We usually would put the low x here and the high x here, but now it's going to be the low y and the high y. So I need to know what this low y value is here, and I need to know what this high y value is here. And again, I don't know what that is at this point, but really it's seeing where the two curves cross each other or where the two curves intersect. And to find intersections, we set the curves equal to each other. So I'm going to go up to the top where there's a little bit of x room here and say 3 minus y squared is equal to y plus 1. Noticing that it's a quadratic, I'll set everything equal to 0. I'll factor, and I'll set each factor equal to 0. So it looks like our low y is negative 2, and our high y is 1. Now we can complete our integral by putting in the upper and lower limits of integration. Negative 2 on the bottom, and positive 1 on the top. Okay, continuing by hand, if I were to continue this process, combining like terms, I'm going to have negative y squared minus y plus 2. Integrating this expression, we're going to get negative 1/3 y cubed minus 1/2 y squared plus 2y. Now first I'm supposed to plug in 1. Then I'm going to have to subtract from that the result when I plug in negative 2. Okay, so I'm running out of room here, so I have to get rid of maybe some of this other work that we had done up top. That's all right. Okay, I'm picking up with this calculation up here where there's a little bit more space. we're going to say negative 1/3 minus 1/2 plus 2 minus, let's see what we have here, 8/3 minus 2 minus 4. With some more cleanup, we have negative 1/3 minus 1/2 plus 2 minus 8/3 minus 6 becomes plus 6. And let's see, negative 1/3 and negative 8/3 is negative 9/3 or negative 3. So we took care of that. 2 and 6 make an 8. And then we have minus 1/2. So now we have negative 3 plus 8 is 5, and 5 minus 1/2 is 4.5. So the area of this region enclosed by the sideways parabola and the line is 4.5.